Okay, good morning everyone. Yes, good to see you all. So we have midterm on Sunday. So today I think we can go through some problems that kind of cover the material that's going to be on the midterm. And let's just go through it. I'm not going to take a break during, we only have a few people here. So first I want to show you the formula sheet. Like you can see here, it's not updated for 10 years already, but physics not changed for the past 10 years. But that means some of the formula is not used anymore, not because it's outdated, it's because we changed the material cover in physics 1. So this part here, this is not on the exam. So don't worry about this Newton's law for gravity. So I mean, you might be confused about the F equal to ma, which is also called Newton's law. But other than that, everything here should be quite useful to you, especially the geometrical formula that you might need for the problems on order of magnitude estimation. So we have one of them. And then we have a set of equations that is for one-dimensional motion. So the formula that we use often is this one, and that one, the first three. The last two, you can derive from these three, but we don't use them as often because it's kind of, you don't need them to solve, because the first three already give you the answer if you use them carefully. Okay, so that's the kinematics equations. Then we have F equal to ma, or we have the relative velocity. So this is written slightly different from what we cover in class, but it's just the minus sign in one of the velocity. So in class we write VAB equal VAO plus VOB, and it's just the last term when you switch OB with VO and you get a minus sign. So that's why the formula is written in this way in this formula sheet. And then we have Newton's law, F equal to ma, usual thing. And then this thing is just to remind you how the friction looks like. But remember, there's very distinct difference between static friction and kinetic friction, even though they have kind of like similar looking equation, but the meaning are kind of different for both cases. Okay, so be careful there. And the right triangle thing, Pythagoras theorem, sine, cosine, tangent, just to remind you what they are. And the quadratic equations, how to solve them, and some unit conversion. So this page will be given to you in the exam paper. So yeah, that's all. Again, don't forget to bring calculator. And that being said, let's just look at the problems that I have prepared for this session then. Okay, so the first question is about reading the graph. So we have 3 particles, and of them, there are 3 different particles. Okay, so and all of them move in x-axis, which is like one-dimensional, with initial velocity of 10 meters per second. So highlight this at t equal to 0. And then we have graph A for particle A, graph B for particle B, graph C for particle C. But they are different quantities. Graph A is the position, graph B is the velocity, graph C is the acceleration. But for all 3 particles, we ask exactly the same questions, which is find the velocity of the particle at t equal to 7 seconds. And it suggests that we should use geometry of the graph, not the kinematics equation. So let's see. So the easiest one is this one, because it's asking about the velocity at 7 seconds. So particle B is, the graph is already velocity, so essentially you just need to read off what is the value at 7 seconds, which is here. And that's minus 20 meters per second. So Vx is minus 20 meters per second for this particle. So that's the most straightforward. Right. Now, the next one is probably particle A. So it's the same time, but the value that you read here, this is not velocity. So for particle A, the answer is not minus 20. So what's the answer? Well, if you have a position and time graph, then the velocity is the slope. So you need to find the slope. So Vx is the slope of this graph here at this point. So, I mean, you can take however large the right triangle to find the slope. So I'm gonna use this particular triangle here, this one. So this is minus 30 meters, and the time here is from 5 to 8, so that will be 3 meters, 3 seconds. So the slope I have is minus 30 meters divided by 3 seconds. So the answer is minus 10 meters per second. Okay, so it's different value from this one because it's a different graph. Okay. And the slope is minus, which is what we expect because it's going down like this. So you expect negative slope. Okay. All right, now the last one, which is particle C. This one I think is probably the most complicated one. So we want to know the velocity here, but to get velocity from acceleration graph, you need to find the area under the curve. So you need to find the area from the beginning until the time that you are interested in. So the area under 0 is negative. So this will partially cancel with the area that you calculated up here. So it depends on how you want to calculate. the easiest, well, not really the easiest, but I think the most straightforward is just to think about this chunk here being cancelled with this. So the only area that you need to count is the green area here. Okay. And you can count how many blocks? 1, 2, 3, 4, 5, 6, and then half a block here, right? So 6.5 blocks. And each block is 1 second in the width and 10 meter per second square in the height. So each block, we are counting the area essentially. So each block is 1 second wide and 10 meter per second square height. So the area, you just multiply the two, right? So the area is 10 meter per second. So 6.5 blocks equal to 65 meter per second. But what is this? Well, the area that you count from this graph, that's going to give you delta V. But delta V is Vf minus Vi. The tricky thing is that the question says that the initial velocity is 10. So we need to add the initial velocity to this equation to get Vf. So Vf is not just 65. That's only the change. Okay, that's only delta Vf. That's the amount of the increase from the initial value. But the initial value is already at 10, so you need to add that. So it's Vi plus Vf. Sorry, Vi plus delta V. So Vi is 10 plus delta V is 65. So the answer is 75 meter per second. So that's the answer for part C, particle C. Is this okay? All right, let's continue. So this is another problem with graph. So let's read what is given here. So we have a train that travels between two stations following the velocity time graph here. It leaves the first station from rest. So from rest means velocity equal to 0, and move with constant acceleration until it reaches cruise speed of 20 meter per second, which is this part here. Okay. And then it stays there for some time, and then it slows down until it stops at the second station. Okay. So essentially it starts from 0 velocity, it's getting faster. Once it reaches here, it stays at 20 meter per second and then slows down and then reaches the destination. So what to do? Well, first question, calculate the acceleration of the time during various parts of this trip. Sketch the acceleration time graph of this train. Okay, so we have 3 parts. I will call part 1, part 2, and part 3. And the acceleration is just the slope of the velocity and time graph. Okay, so acceleration is the slope of velocity time graph. So calculate the slope of the first section. So I can use this triangle here to calculate the slope. So it's a acceleration during the first part, so I write it as A1. So A1 is delta V divided by delta T. So the triangle that I use here, delta V is the height of the triangle, which is 20 meters per second. And delta T, which is the base of this triangle, that's going to be 100 seconds. So it's 20 meters per second divided by 100 seconds. That's going to be 0.2 meters per second square. So that's this part here, the first chunk. Okay, 0.2 meters per second square. And then the second part, there's no change in the velocity. So acceleration is 0. Okay, that's probably the easiest part. So A2 is 0. Now A3 is the same kind of calculation as A1. So we calculate this triangle here. Except that you can see that the acceleration must be negative because the slope is going down, the velocity is decreasing. So that's going to be minus 20 again, that's delta V, meter per second. Okay, because eventually it's going to stop, so delta V is negative. But the time taken is longer here. The time taken for the last part is 200 seconds. So altogether you get minus 0.1 meter per second square, something like this. Okay, now part B, what's the total distance between two stations? So this one just asks the area under the curve of this whole thing. That's the displacement, but this is one-dimensional motion, so displacement translates directly to distance. And it's also because you don't turn around, so there's no complication of that. Okay, so so the most straightforward way is just to use the formula to calculate this kind of shape. And I think the formula is 1/2 times the height times the I don't remember if it's like the average of the two. Okay, I don't remember the formula, so let's do it differently. So you can divide this into three shapes: rectangle for part 2, triangle for part 1, another triangle for part 2. Okay. So the distance for part 1, which I call D1, that's going to be 1/2 times the height, 20 meters per second, times the base, which is 100 seconds. Okay. So this is going to be 1,000 meters. Okay. So you can see that the formula works out okay. Second here cancel with each other. So distance has to be in meters, right? So that looks good. Now the second part is just a rectangle. So you just multiply the height with the base. The base is from 400 to 100, so that's 300 seconds. So that's going to be 6,000 meters. And then the last part is also a triangle, so it's 1/2 times 20 times the base, which is 200 seconds. Okay, so it's 400 to 600 seconds, so that's going to be 2,000 meters. So sum, which is D1 plus D2 plus D3, that's going to be 9,000 meters or 9 kilometers. So that's the answer. Okay. Okay, if this is fine, then let's move to the next question. Okay. So this one is quite a simple one. I just want to make sure that we know how to work with the angle of the vectors. So we need to find the force vector that make the knot not moving. So the easiest one is to decompose all the forces into x and y component. So this is 5 newtons, this is 3 newtons. And the unknown one I will just draw with different color here. Just write F like this. Okay. So the exam probably asks like what is the force vector required to make the knot stationary. So your answer will probably have this form. So some number I plus some number J, and then the whole thing in the unit of newtons, something like this. Okay. So your job is to find out what's the number in front of the I and J component. So whatever this force is, it has to balance the other two. And we know that this angle is 120, right? So from the vertical line, it's just 30. As you take away 90 degrees. So you decompose the 5 newtons into vertical and horizontal component. And with this, you can forget about the original force. The vertical one will be 5 times cosine of 30 degrees. The horizontal one is 5 times sine of 30 degrees. Okay. So again, notice that the vertical is cosine because of the way that I use the angle. I think it should be quite clear by now. So let's calculate the vertical. The vertical one, this is 4.33 newtons. And horizontal to the left, sine 30 degrees is just half. So that's equal to 2.5 newtons. Okay. So whatever this unknown force is, the vertical component which is pointing down, this one has to be cancelling with 4.33. So that's going to be negative 4.33, right? I think. And then the horizontal component of this force must be, when you add with 2.5, that's equal to 3. So that's 0.5, right? But it's 0.5 to the minus x direction. So it's going to be minus 0.5 j, like this. So this will be the answer of this force. In principle, this is already a perfectly fine answer, but I mean, if you want to find out like the magnitude of the force, you have to calculate by taking the square root of 0.5 square and 4.33 square. Which is 4.36 newtons. Okay. And for the direction, you can, if you want, you can calculate using, the arctangent of the angle, which should be pretty straightforward. So you can do that. Okay, so again, don't forget that if the questions ask about vector quantity, then your answer has to be vector, like velocity, acceleration, forces, even displacement, okay? Unless it's stated clearly that you want just the magnitude or just the direction. But in general, if the question asks what is the force, force is a vector, then you need to answer fully like this. Okay, let's continue. So another topic that surely going to be covered on the exam is projectile motion, which is a while ago that we covered this, right? So we have like an object that is launched on kind of the unknown planet. So essentially the whole thing of this problem is that g is not 10 meters per second square, because that's for the Earth, we are not on the Earth anymore. So I want to find out like what's the g value of this planet Exeter or something. And even though you don't have g equal to 10, you're going to have g equal to some value. The trajectory of the object is still be a projectile motion. So let's see. So you have the trajectory here. At the 0 second is when you launch it. 1 second is here. 2 seconds is here, which reaches the highest point. So at 2 seconds, the velocity will only point horizontally. That's the definition of the highest point, right? Because if it still have some vertical component of the velocity, that means it has not reached the highest point. So at the highest point, the velocity must be pointing horizontal. And then 3 seconds, which is after the highest point, the velocity start to point down like this. So I really like this question because it's kind of asking really the important conceptual questions about projectile motion. So question A, determine the ball's velocity at t equal to 0 second, 2 seconds, 3 seconds. 1 second is already given to you. So it looks like, how I'm gonna calculate that because I don't know what's the g value. Okay, But one key information is that from 1 second to 2 seconds, you know that the vertical component of the velocity get reduced to 0. So you can calculate the change in the velocity from 1 to 2 seconds. So from t equal to 1 second to t equal to 2 seconds, delta v in the y component, which is the vertical component, is 0 meter per second, right? That's at t equal to 2, minus velocity in the y direction at t equal to 1, which is 2 meter per second. So that's minus 2 meter per second. So the acceleration in the y direction, which is delta velocity in the y direction divided by delta t, will be minus 2 meter per second divided by time, which is 1 second, and that's minus 2 meter per second squared. So every second, the vertical component velocity will get reduced by 2. And it's a projectile motion, right? So all the acceleration is in the y component. So this will also answer question B. But let's answer question A fully first. So at t equal to 2, the velocity only has horizontal component, but horizontal component is unchanged for the projectile motion. So here you can write 2I meter per second and no j component because that's the highest point. And this number is exactly the same as this number because again, there's no acceleration horizontally. So Vx stay the same. And then at 3 seconds, velocity at 3 seconds, horizontally it's still the same, which is 2. But vertical component, because every second gives you minus 2, right? So now it's going to add minus 2j meter per second for velocity at t equal to 3. Okay, so we answer this 1, 2, 3. Now we need to answer t equal to 0. So t equal to 0, again, horizontal component is always the same, 2. But vertical is, so from here to here, the vertical velocity will get reduced by 2. But since you have 2 here, then here you probably have 4. Okay. So that's going to be 4.0 meter per second for the y component. So this is the velocity. Okay. Again, the x component is unchanged throughout the motion, but the y component start out with 4, get reduced by 2, so it's get to 2 here, get reduced by 2, get to 0, reduced by 2, now become minus 2. So that being said, that means the g value on this planet is 2 meter per second square. Okay. What is the ball launch angle? The launch angle is essentially just asking that if the velocity at 0 second is this is j, 2i plus 4j, what would be the angle here? So tan of this angle is the y component divided by the x component, so which is 2. So the angle is just arctan of 2 which is 63.4 degrees. Okay, so again, this problem covers like all important conceptual idea that is important in projectile motion. Okay, if there's no question, then let's move on. Still at projectile motion, but this one probably involves a little bit more calculation. So we have an object launched from the ground at the angle of 60 degrees. So this is 60 degrees. And the initial velocity 20 meters per second. So with this, you can write down the initial velocity vector fully. And the distance is 24 meters. And the height is 7 meters. So the question is whether the ball can reach the person on the top of the building. So it's quite interesting. Like, what do you check then? Like, I mean, normally you are given a lot of things and you can just calculate, right? Right here is kind of like a little bit open-ended in the sense that you need to somehow check whether the ball is reaching the top of the building. So one way to check is that where is the ball where the horizontal distance is 24 meters? Like, you just check the position of the ball when it reaches this line. If the height of the ball is anything higher than 7, that means it's one of these, right? Then it's gonna clear the top of the building without any problem. But if the ball is lower than 7 at this line, then it's gonna hit the building. So that means I just want to check the position of the ball vertically when the horizontal position is at 24. That's my plan. So let's do that. So the velocity is 20 meters per second for the magnitude and then 60 degrees for the angle. That means I can write the vertical and horizontal component to be v cosine 60 and v sine 60 for the vertical and horizontal component. So that means v initial is 20 times cosine 60 for the I component plus 20 times sine of 60 for the j component. And the whole thing is in the unit of meter per second. So I cosine of 60 is a half, so half times 20 is 10. So it's 10 horizontally plus sine of 60 times 20, that's 17.3 in the J component like this. So again, I want to check where the ball is when the ball has traveled horizontally for 24 meters. So I need to find like what's the time when it reaches this line here. So the time to reach this plane, this line here, is the horizontal distance, 24 meters, divided by the velocity in the horizontal component, which is 10 meter per second. Okay, so again, this is Vxi, and that's going to be 2.4 seconds. So the ball reaches this line here at t equal to 2.4 seconds. So what I want to check is where the ball is vertically at this same moment in time. And then I can, compare with the 7 meters, which is the height of the building. So where is the ball vertically at t equal to 2.4 seconds? So here you're going to use the formula for the y displacement. So yf equal yi plus 1/2, plus v I yt plus 1/2 ayt square. And the initial height is 0. I didn't talk about this, but we can set it to 0. So 0 plus vertical velocity, which is 1.3 meter per second, times the time, which is 2.4 seconds, plus the 1/2 acceleration, which is minus 10 meter per second square, times t square, which is 2.4 seconds square. So let's calculate this. So that's going to be 12.72 meters. Okay. So the ball is 12 from the ground at t equal to 2.4 seconds. So it's going to clear the building. Another thing I want to make sure that you all know how to calculate is what is the height, the highest point of the ball of this trajectory. So how do you do that? Well, to calculate the maximum height, you need to know what time that happened. So the maximum height is when the velocity is only horizontal. So you just need to find out the time where the vertical velocity is 0. So Vy equal Viy plus Ayt. So this equation just gives you the value of the velocity in the y component at each time. So initially it has 17.3 meter per second. and the acceleration is minus 10 times t. Okay, so the whole thing is in meter per second. So what's the time that it reaches the height? Well, it's when you put this equal to 0, then time will be just 1.73 seconds. That's the time where it reaches the highest point. So notice that this time when it reaches the highest point is before the time where it reaches the building. So you know that the way that the figure draws in terms of the trajectory is already correct. It reaches the highest point first and then curve down and then reach the building. Because if you kick it hard enough, it also might be possible that when it reaches the building, it's kind of still on the way up and not reached the highest point yet. If that's the case, the time when it reached the highest point will happen after 2.4 seconds, which is not what we have here. Okay, so the picture is kind of already accurate in this sense. So what is the highest point? Then you just put this time back into this equation to calculate yf at t equal to 1.3 seconds. So yf equal yi plus viyt plus 1/2 ayt squared. So it's the same formula, just different time. So I put in the number, and if our calculation is correct, then the number you get here should be larger than 12.72. Let's see if that's the case. So this term gives you 30. This term gives you 15 minus 15. So altogether you're going to have 15 meters, which is higher than 12.72. Okay, so the height is 15, so it reaches 15 and then curves down to 12 where it hits the building. But in any case, it's always going to be this pattern, like you find out the time where the thing that's happened is what you want, and then you use that time to calculate the other thing. Okay, so the tricky part is probably just like what condition that you're going to use to find the time that you're interested in. Sometimes it's kind of straightforward, like the time where the ball hits the ground. Sometimes it's not so straightforward. Okay, let's move on. So this is one of the past exam questions where we have two things heading towards each other. So we have Ethan Hunt, which is Tom Cruise, and Solomon Lane going against each other like this. And one of them is accelerating, the other one is constant speed. So Lane is constant speed at 40 meters per second. And Ethan Hunt start from 0 but accelerate with 2 meters per second square. And the distance between the two is 480 meters. And we need to find out where do they crash in the middle here. So it's kind of, like a standard problem in one-dimensional motion. So how do you calculate? Well, the crash happened when the distance traveled by the two parties added together give you 480. So I can write the equation for Hunt, which is with acceleration. So the distance or the displacement that Hunt acquire for any given time, because it's accelerating, so it's going to be VIT plus 1/2 AT squared. But Hunt start with 0 velocity, so doesn't have this term, so that term is 0. So it's only 1/2 AT squared, which is t squared if you plug in the number for the distance that Hunt traveled. For lane, distance is only from the velocity part because there's no acceleration. So VIT plus 1/2 AT squared for lane is actually the second term that is 0 for lane. So that's 40 times t. And the crash happened when the distance of the two are 480 when you add together like this. So you have a quadratic equation that has t squared plus 40t equal 480. And then you need to find the time. So you need to rearrange a little bit. So for t squared plus 40t minus 480 equal to 0. And then you use the formula in the formula sheet, right? There's the quadratic equation, how to solve. Then divide by 2. Okay, then calculate this. So it's minus 40 plus minus 59.3 divided by 2. And surely the time we want is positive time. So it's minus 40 here, so it's going to be plus sign here. And then divide by 2. So the time is about 9.66 seconds. So that's the time where the crash happened. So if you can also solve this by drawing the graph, but mathematically it's not going to help much. You still need to solve quadratic equation. So at t equal to 0, lane is 480 meters away, and he is going towards the origin with constant velocity. So the graph for lane gonna look like this. But Hunt is accelerating, so the graph for Hunt will be curved. So it will look something like this. And the crash happened here. That's what we just calculated, 9.66 seconds. Okay. So essentially what we did here, geometrically, is just to find the intersect of the two lines. Same math, but maybe a little bit different in the visualization. Okay, so what's the distance traveled by hand from t equal to 0 until the crash? Well, we just need to substitute t back into the equation for hand, because distance for hand is just t square, so it's just 9.66 square. 9.66 square, which is 93.3. Now, just for the sake of checking, let's calculate the distance for lane, which is 40 times t. So it's 40 times 9.66, which is 386.4. And if you add the two together, you get about 480. So our calculation is probably correct. Okay. So there are many things that you can ask for this, like how fast are they going when they crash? And surely they don't have to be at the same speed, okay? All right, let's move on. Unless there's more questions. Okay, let's do this one. This one I also really like, because it's a simple question that show you if you understand how friction works. So we have this. This is kind of the modified Atwood machine that we talked about in class last time. So we have two blocks, and then one of the block is on the incline, the other one is hanging, and they are tied together with a string, and both of them are 20 newtons. So this one is 20 newtons. This one is 20 newtons here. No, it's 20 newtons times sine of the angle. So 20 newtons is pointing down, but the normal force kind of partially help with that. So this is 20 newtons times sine of the angle. So it's probably good to calculate the geometry of this triangle first. So A is 3, B is 4, and the hypotenuse C is 5 meters. This is just a standard, Pythagoras number that probably you all remember. So sine of the angle is A divided by C, which is 3/5. So that means the force pulling down this weight along the incline is 20 times 3/5, which is 12 newtons. Now the hanging mass, well, nothing moves, right? So all the forces on each mass must be 0. So the hanging mass is being pulled down by the weight of 20 newtons. In order for it to not move, the tension must be pulling up also at 20 newtons. But the string is the same as the one attaching to the other mass. So the tension on the other mass must also be 20 newtons, and it has to pull up like this. But if these are the only two forces on this mass here, it's sure gonna move up, because the sum of the force is not 0. but it doesn't move up, so it must be a third force that helps canceling everything, right? And that's going to be static friction. Again, remember what I told you in class last time, like how do you know which way static friction moves? Well, imagine if you don't have friction, which way it's going to move. If you don't have friction, you're pulling up 20, you're pulling down 12. So surely the mass is going to move up along the incline. So friction must be preventing that. So friction must be pointing down like this. And how much it is pointing down? Well, it's whatever it is to help cancelling with 20 newtons plus this. And just, you know, I think it's clear that the answer is 8. Okay, so down 12 plus 8 equal to 20. So everything cancel out. So nothing move. Okay, let's move on to this one, still inclined plane. So we have an object which is 2 kilograms and it's moving up a ramp with initial speed of 5 meters per second. And we have the angle equal 30 degrees. And we have coefficient of static and kinetic friction given to you, 0.8 and 0.4. So just asking two simple questions. What's the acceleration when it's sliding up? And how far does it go up along the ramp? Okay. So if I draw the block, maybe I'll draw it here. There will be mg. There will be the normal force. And it's sliding up. So we know that the friction that we are interested in is the kinetic one. So Fk. So it's sliding up. That means Fk will be opposing the motion by pointing down. And the usual thing, we kind of did this without saying much last problem already, is to decompose mg, right, into mg sine and mg cosine. Mg cosine. And then we can forget about the original mg. So the normal force will balance mg cosine. It's not so relevant in this. Well, it's kind of relevant because we need to find Fk, which is equal to mu k times n. So we know that n equal mg cosine. And for the acceleration, well, if we say that going up along the ramp is positive direction, then both mg sine and kinetic friction are pointing in a negative direction. So both gonna slow down the object. So if you write sigma f equal to ma for the object in the direction along the incline, where going up is positive, then the force will be both negative, right? minus Fk minus mg sine equal ma. And kinetic friction is mu k times n. So it's mu k times n minus mg sine equal ma. But we already have n here, which is mg cosine. So it's minus mu k mg cosine minus mg sine equal ma. And you can cancel out all the mass. Okay, so actually the problem doesn't even need to give you the mass because it's cancelling itself. So the acceleration is the negative value of minus mu k cosine minus g sine. And if you want to put in numerical value, it's minus 0.4 times cosine of 30 degrees minus 10 meter per second square from g and then sine 30 degrees. Yeah. Good. Here, right? Kg. So another factor of 10 here. 0.4 times 10 times cosine. Thank you very much. Times 10 times 0.4. So the first term is minus 3.46. The second term is 10 times sine of 30 degrees, which is a half. So that's 5. So altogether it's minus 8.46 meter per second square. Okay. Again, it's negative because I choose going up along the incline to be positive. So this thing will slow down the mass. So that means I can calculate the second question, which is how far does the object move along the ramp. So the displacement along the ramp is initial velocity plus 1/2 at squared, usual formula. But this is where this formula is probably not the most convenient because we don't have like time in, we don't, if we know already the time, then it's fine. So it's probably better if we use a different formula, which is Vf square equal Vi square plus 2As, which is one of the formula in the formula sheet up here, this one. Okay, let's go back. So this is good because there's no time variable. And how far does the object move up the ramp? How far means eventually it's going to stop. So Vf will be 0. Vi is the initial velocity, that's 5 meter per second square, plus 2A, which is minus 8.46. And you see that having a minus sign is good because otherwise you cannot solve for s, the distance. And then you just solve for s, it's 25 divided by 2 divided by 8.46, 1.47 meters. So that's the answer. Well, the acceleration is negative, but s, which is the displacement, must be positive because it's in the positive direction. Is this okay? You okay? Okay, good. Two more. Okay, this one is one of the Canvas homework, which is gone already. But it's one of the more challenging problems, so I just want to make sure that we know how to calculate. Okay, so imagine that you're in charge of figuring out the maximum speed of a very foggy road. Consider a road where we cannot see anything beyond 15 meters. And we have reaction time of 0.3 seconds, which is standard reaction time. And the deceleration from pressing the brake, which is negative acceleration, is minus 10, it's 1g. What should be the speed limit of this road in meter per second? So essentially, you must stop before 15 meters because the worst case is after that you're gonna hit something. But the point here is that there's the reaction time of 0.3 seconds. Reaction times means the time where you kind of freak out and you didn't do anything. So the car will still be moving. And then after that reaction time, you slam the brake and then you start to decelerate. So the motion is divided into two parts. The part where it's still going without deceleration and the part where you decelerate. And let's call the first part to be d1 distance and the second part is d2 distance. And the thing is that d1 plus d2 must be 15 meters for the worst case. That's the idea. I mean, it's better if you stop before 15, but this is kind of, the worst that can happen. So if you are traveling with some velocity v, this v is what we're going to calculate. But we don't know that yet. So we just assume that it's just v. We can calculate the distance d1 by knowing that the time that you travel for this first chunk is exactly the reaction time, which is 0.3 seconds. So 0.3 seconds times the velocity v, that's d1. And we don't know v, so we can't do anything else. So this becomes 0.3 v. Okay. And then we do the second part. The second part, initial velocity is still v, but now we decelerate. And then eventually the velocity here will be 0. So we can calculate d2. So d2 is vi, well, okay, I think this is also the time where we should use a different equation, which is vf square equal vi square plus 2a d2, because we don't have information about the time here. So vf is the velocity at the end, which is 0. vi is the velocity here, which is also the same velocity that you start with, so it's just v. And plus 2, a is minus 10 meter per second square times d2. So 0 equal v square minus 20 d2. So d2 is v square divided by 20. Okay. So now you just need to add them. d1 is 0.3 v, d2 is v square over 20, and this has to be equal to 15. So you just need to solve for v square and it's quadratic again. So just multiply 20 by throughout the equation, and that's going to be minus 300 maybe, like this. So v is another quadratic equation by this. So minus 6 plus minus 35.1 divided by 2. And we again need positive velocity. So 14.6 meter per second. It's the fastest you can go without crashing. Let's do unit conversion quickly so that you know, because you don't drive in meter per second, you drive in kilometer per hour. So 14.6 meter per second going to kilometer per hour. So how do you do that? Well, 14.6 meter per second multiplied by the first factor, which is 1 kilometer divided by 1,000 meters. And then I want 1 hour down here. That's 3,600 seconds, like this. So second cancel with second, meter cancel with meters, then I have kilometer per hour. So it's 14.6 times, which is 52.5 kilometer per hour. Okay, it's kind of fast, but it's not too fast. I mean, depending on where you're driving. If it's on the highway, then it's kind of slow. It's kind of the similar flavor of the Ethan Hunt and Solomon Lane problem that you need to set up for both, and then you solve quadratic equations. Okay, I think we have the last one. Last one is also one of the past problem. So we have a block on another block. So the smaller block is small m, the bigger one is big M. All surfaces are rough and of similar kind. So the coefficient for static kinetic friction are mu s and mu k. And someone is pulling the top mass to the right with tension T, going to the right. Okay, so if nothing moves, what is the magnitude of static friction between M and the ground, which is this one here? Well, I can say that the answer is not mu s times n. That's the max value possible, but we don't know if we are pulling at the max or not. The only thing we know is that nothing moves and you're pulling at T. So if you draw the diagram for small m, okay, you're pulling to the right with T, but small m doesn't move, so some horizontal force must cancel out T. And that's the static friction between small m and big M going to the left, Fs equal to T, like this. Okay, that's for the small mass. Now for the big mass, the big mass is in contact with small mass, And this static friction here is the force that big M is exerting on small m. So that means you're going to have a reaction force that small m is acting on big M. And it's going to be opposite direction. So you're going to have this friction Fs also equal to T from small m that is trying to pull the big mass to the right. But big mass also doesn't move. So that means there must be another friction between the ground and the big mass that is cancelling with that. So you have another static friction which must be equal to T. That's preventing the big mass from moving. So if nothing moves, then the static friction between the big mass and the ground is also T. Okay. So it will be also easier if you think about the whole mass as one chunk, because there's no difference, right? Nothing moves means you can just glue them together. And if you're pulling with T and it doesn't move, then the friction must be also T, tension here. So for question B, now it's a little bit more complicated. The small mass moves, but the big mass doesn't move. What is the acceleration of the small mass? Well, the big mass now is, you can think of it as part of the ground, right? So the small mass move, that means friction you use here is kinetic friction. So Fk, and then tension to the right. And you also now need to consider the normal force because you need Fk and then mg. Okay. So the vertical force must be balanced. So the normal force is equal to mg. That means Fk, which is kinetic friction, is mu k times n, which is mu k times mg. So the net force horizontally is tension minus this force. So from sigma F equal ma, sigma F is just tension minus kinetic friction, mu k mg, and this is equal to ma. So we can solve for A easily. That's just tension divided by m minus mu k times g. So that's the answer. And I think that's all I want to talk about for today. So before we finish, again on Wednesday there's no class. You have exam on Sunday. I won't be here, but the other two instructors will be around, so you can ask them if there's any problem with the exam. Don't forget calculator. Formula sheet, I already showed, so review it again, what is included, what's not included. And check the time and the room for the midterm. And good luck everyone, and I will see you on Monday then. Okay? All right, thanks for coming. I'll see you later.